Assalamualaikum warahmatullahi wabarakatuh. My name is Siti Nur Hanisah binti Noor AZMI with student number 2019-287-494. In this video, I will explain about experiment T3, which is determination of nozzle efficiency. First, the objective of the experiment. The first objective for this experiment is to study the characteristic of the nozzle and the parameters that affect its efficiency. The second objective of this experiment is to study the relationship of air mass flow rate. The apparatus that we will use in this experiment is the Hilton Nozzle Performance Test Unit, which is this machine. Next is the main component of the apparatus, which is long chamber, nozzle, pressure gauge, thermometers, flow meters, valve. The long chamber. It will be a 50 millimeter diameter, which is stainless steel, and it around 300 millimeters long and T-shaped. The end cover is held in place by stainless steel bolts and sealed with a O-ring. A drain valve is installed inside the chamber. Nozzle. The throat diameter of the nozzle is nominally 2.0 millimeter. There is one convergence for 4 convergent divergent lines with exit area or throat area ratios of 1.2, 1.4, 1.6 and 2.0. 10-degree divergence are included. For the pressure gauge, it is to monitor intake and chamber pressures. Two pressure gauge ranging from 0 to 1100 kilopascal are required. For the thermometer, in this machine, we will use three of 150 millimeter long mercury in glass thermometers that were used to measure inlet and chamber temperatures. Flow meter. The air flow meter range is measured using a variable area type meter. It is calibrated for use in a typical environment. Other conditions are resolved with correction. Diverter valve. For the diverter valve, it is used to channel air to a nozzle placed in the chamber's wall for nozzle efficiency testing, or to a hollow cantilever for jet reaction testing. Needle valve, to provide precise control over nozzle inlet pressure. For the back pressure valve, it is used to regulate the pressure inside the chamber. For the micrometer adjustment screw, it is used to change the voltmeter value, and this needs to be set as 0. Oh, sorry, there is some typo here. It should be VOLT, voltmeter value. For the experiment procedure in this experiment, the first step, before beginning the experiment, check the contacts. The contact should be clean, and the battery also should be working fine. The impact head is attached at the end of the cantilever, and furthermore, ensure that the micrometer dial is 0 and that a cantilever load or deflection graph is available. First, you need to close the air inlet control valve and open the chamber pressure control valve. The second step, unscrew the knurled nut at the upper right corner of the chamber, remove the nozzle mounting sleeve and install the nozzle number 1 into the unit, which is here. The third step, turn the diverter valve handle to the upward position. The fourth step, adjust the inlet control valve to provide a constant air inlet pressure of 600 kPa gush when the chamber pressure control valve is completely open. Open the chamber pressure control valve here and we can see the inlet pressure of 600 kPa here. For the fifth step, turn the micrometer adjustment screw until the voltmeter and the light show contact. That contact has just been made. When the contact has been made, the voltmeter, which is at this indicator, will be turning on, and there will be some different value here, which can be meaning that it is functioning well. The most sensitivity is attained by the adjusting the screw such that the voltmeter reads around 0.5 volt. The sixth step of this experiment procedure is to record the pressure, temperature, air mass flow rate, and dial reading. Next, increase the chamber pressure to about 100 kPa gush and repeat the preceding step, which is the sixth step. Repeat the test at various chamber pressure with 100 kPa increment, ensuring that the inlet pressure stay constant. Last but not least, repeat the whole experiment by using the nozzles. Using the other nozzles. For the safety and precaution for this experiment, first, you need to make sure that all the experiment procedures is followed so that there is no error happen during the procedure. Second is, make sure to use ear protection like and earplugs because the experiment produce noisy sound.
This is for part 2, step 2, which is the calculation. So first we will do the table based on this table from the left sheet. So this is table for nozzle 2. Number 1, 2, 3, 4, number 5, 6, 7, and 10. Okay, and then first is in the gosh. One over okay, this one. So this will be subscribed and done. Okay, on top. Okay, first to inlet temperature, which is the 1 over C. So insert symbols. So let's close. Okay, this one subscribe. Okay, and the temperature. Temperature. Gosh, salt B2 over KN negative 2. So this one subscript. This one is superscript. After that, table temperature T. Copy T2 and then cantilever deflection, insert symbol. Yes, and then let's read observe symbol. And over time after K2 as one. So this one is superscript. This one also superscript. And after that, fill in the table. So here is 600, and then to 4.5, to 4.0, to 4.5, to 4.5, to 4.5, to 4.5, to 4.5. Okay, and then this one should be okay, and then the chamber pressure gauge 0, 100, 200, 300, 400, 500, 600. And then for the chamber temperature, to 5.0, to 4.0, to 4.5, 24.5, 24.5, 24.5, 24.5. And let it be in this format. And then for the cantilever deflection, based on the experiment, for 54.0, 46.0, 38.0, 30.0, 23. Oh, sorry. This one is 30, 23, 16, and 0 for this point. Okay. Next is the MS flow rate. Observe point is 0.0052. 0.0051, 0.0052, 0.0052, 0.0005, 0.0046, and 0.0012. Okay, this is observation table, and then we will do the derived result table. So for the derived result table, derived right, 1, 2, 3, 4, 5, 6, 7, and then so first is MS flow rate plus this one should be cancel. Substitute. Okay, this one should be corrected. And then next is inlet pressure absolute. To see, to be absolute. This one is subscript. This one is the B one should be subscript. Okay. Next is inlet temperature absolute. Inlet temperature absolute D1 over T. So this one should be subscript. Okay. Okay, then chamber pressure. Absolute. And then should be subscript. This one should be superscript. And then chamber temperature. Absolute. And then just copy this here. This one should be D2. And superscript. Okay. After that, overall pressure. RP. Okay. Then is impact or jet reaction velocity. Reaction force. This is from graph, and we will take a look after this in the lab sheet. So F over N. And then for the next is just velocity, which is C2 over S -1. So 2 is mini, so the 2 subscript and superscript. Okay. And then next is theoretical jet velocity. Which is 2 over M per MS -1. So subscript and superscript. Next is nozzle efficiency, which is the unit needed. one. Okay. Okay, this one here. This one here. Okay. And make it like this. And then next is the extra one, which is density. 1, 2, 3, 4, 5, 6, 7, and then exit area. Okay. These two we will use to do some calculation in direct result. So I will place it here beforehand. The first is the inlet pressure. I will do the inlet pressure first, which is the P1 here. We will place it with 101.325. Then write it. After that, the inlet temperature, which is we take it from the inlet temperature here, plus 273 to change it to Kelvin. So enter. Next is chamber pressure. So chamber pressure, I will use the chamber pressure gauge, plus it with 101.325. Okay, here, drag it. After that, chamber temperature, also it's the same with the inlet temperature, which is we need to change it to Kelvin. So T2, which is chamber temperature, we will add 273. Drag it. So for the overall pressure ratio, equal to absolute chamber pressure, which is this one will be divided by absolute inlet pressure. So enter. Okay. So this one I think I will use just 3.5. So next is impact or jet reaction force. This one will refer to this graph. Okay, this one. So based on this, based on the graph, so we will see it from cantilever deflection. So 54 is around here. So a line up straight, and here should be 2.225. Next is 46. 46 is around here, so here. So go up straight, and it is around 1.9 or 1.9. For this one, maybe I will use. Okay. So next is 38. So 38 is around here. So up straight. It is around 1.6. Am I not mistaken? Yeah. So 1.600. Next is 30. So 30 is here. So it should be around 1.225. 1.225. Next is 23. 23 is 1. Yeah. So it's around 0.9. So 0.9. So next is 16. So 16 is around here, and it should be around 1.6 something. So 0.6. And then last but not least, 0. So 0 is here, and then 0 as well. So 0. Okay. And next is so from here I will do the this one first. So for this one, we
see that the equation here, which is yeah, square root 2 gamma over gamma minus 1 RT1 in bracket 1 minus RT gamma minus 1 over power of gamma minus 1 over gamma. So from this equation, SQRT square root and then 2000 times 1.4 over 1.4 minus 1 times 0.287 in time inlet temperature, which is this one, yes, this one in time mixed with in bracket 1 minus RP over this and power of in bracket 1.4 minus 1 over 1.4. So enter. Yes, okay. Drag it and I will take 3.9. So next is I will find the density first. It should be 2 over 32 times 0.287. Take it 3 point. Okay, and then for the epidemic, it should be 1.2 times pi. Oops, sorry. 1.2 times in open bracket pi and 0.2 and 0.02, which is the nozzle, the truth diameter, power of 2, close the bracket, and divide by 4. And yeah, okay. So I don't know. Okay, after this, okay, this one. So make it easier and simple. And then I will start with the MS flow rate. So density times exit area times theoretical jet velocity equal to this one this number 3 point behind, so drag it. For the jet velocity I will for the jet velocity is this one impact or jet reaction force over overall pressure ratio. Enter. This one make it oops. Okay. And then drag it to the back. And then for the nozzle efficiency is equal to bracket jet velocity power of 2 over theoretical jet velocity power of 2 close the bracket and times 100. And then but okay, from here I will next to the graph. So insert choose line graph and then put it here. So select data, add series value, take it from corrected MS flow rate, and okay, this one is
take it from overall pressure ratio. Okay. This is the experimental line. Next, I will add for the observe. So the series value I will take it from observe MS fluid, and this one I will also take it from overall pressure ratio. Okay. As this title, maybe only this one. So this one. Okay, for the track title is MS fluid versus pressure ratio. This one. Okay, and then inside go. This one inside. Oh, yeah. So go inside this one, and then for the pressure ratio is RP. So first this one, and take it from here. Proceed. Maybe RP. This one should be. Okay. For this one, this title is pressure ratio RP. Okay, next this one, this title is MS flow rate. Insert symbol, this one insert close, and then yes. Okay, one more graph should be select data at and I'm gonna take this one. Okay, we did this and overall pressure. Okay, and then this title should be nozzle efficiency versus pressure ratio. And I should copy it from here. So base versus pressure ratio, which is RP, and as usual, B is subscript. So okay, and then add the SS title, trend line, and then okay. So this one is copy, and then this one copy, paste. Okay, that's all.
For the conclusion in this experiment, this determination of nozzle efficiency experiment has achieved its objective, which is to study the characteristics of the nozzle and the parameters that affect its efficiency, and to study the relationship of MS flow rate. Furthermore, all the data needed from the experiments, such as jet velocity, overall pressure ratio, and nozzle efficiency, can be obtained by doing calculations. Overall, the experiment can be considered as a success. This is the recommendation for this experiment. First, make sure that all the apparatus and all the parts of the apparatus can be functioning well, so that there is no systematic error during the experiment. Second, make sure to be extra careful in taking the reading of the data value, so that the calculation of the experiment can be more accurate. Third, make sure that the eyes are parallel with the measurement during the measurement intake or measurement reading so that parallax error can be avoided during the experiment. Last but not least is application. This nozzle efficiency experiment actually can be used in steam turbine, gas turbine, water turbine, and jet engines, which is jet propulsion. It is also used for flow measurements such as in bathymeter. It also can be used to remove air from a condenser. The injectors for it also can be used for injectors for pumping feed water to boilers. That's all from me. Thank you.